All right, guys, so now let's talk a little bit about the science section, okay? So the science section is probably one of the most feared section on the ACT. More so because students are like, well, math, reading, and English I can handle, but science, dude, science is not my favorite subject. Or, there's just a lot of science on this that I just don't understand. But the good news is that the science section isn't really about the science. It's more about here's a whole bunch of facts, figures, tables, charts, graphs, and drawings and things, and pick the best answer choice that you can, the closest, the answer choice that you can refer the closest to. Okay? So just before we jump in, let's talk a little bit about some of the fun facts, and I call them fun because they are fun facts about science, okay? So the science test gives you 35 minutes to answer 40 questions. Very similar to the reading section, right? Whoa, lots of questions, not enough time, right? But the good news is that like the English section, like the math section, like the reading section, students generally end up being able to pace themselves pretty well on this section. Right? And the order of the passage is going to vary, but there's really just three large formats, or three general types of formats that we're going to see. The first is just the charts and graphs, right? These are our scientific experiments that have lots of charts and graphs and figures for you to work off of, and it's just a lot of information. These generally, there are about 12 to 16 questions that refer to these. Then there's the experimental questions, right, or experiments questions, where the scientist conducts an experiment, or multiple scientists conduct a certain type of experiment, and they all present their findings, and we're supposed to kind of figure out what they are. And then we have the fighting scientists, and these are, as the term suggests, is when two or more scientists are arguing about the same topic or proposing different theories or different ideas supported by their premise as to why their viewpoint is a certain way. Okay, so the first thing to kind of keep in mind and the first thing that a lot of students end up doing with regards to the science section is that they want to read the entire passage. They want to read the experiment. But like the reading section, right? Reading the entire thing doesn't answer a question for us. Okay, we need to get a little bit more specific. We need to be more efficient. I mean, come on, we don't have a lot of time, right? So our whole kind of standard, our whole kind of strategy is based on this idea of defining the right answer is based on using the trends that appear within the questions or within the figure or within the viewpoints, right? Using a lot of common sense, and this is where the inference kind of works on, right? Common sense meaning that if something is doubled, then the results might be doubled unless there's something else in the passage to tell me otherwise, right? So common sense, and also by using the scientific method, that common sense kind of comes into play. And then the part that most students are like, oh my God, is the outside knowledge. Now, granted, there are a few questions regarding outside knowledge, but nothing too specific, and they are not so frequent enough that not knowing a lot of science isn't going to hurt you. As a matter of fact, if you're dealing with an outside knowledge question that you have no idea about, feel free to skip it for now. Okay? Otherwise, even those questions can be answered by using the trends that we have, as well as common sense, or even just breaking the questions down into smaller pieces. Okay? So before we go into all of that, we have to discuss the personal order of difficulty, right? Because the personal order of difficulty is this thing that haunts us no matter what passage, no matter what section that we're in, right? And like the English section, like the reading section, like the math section, right? There are certain questions that are easier for us and certain questions that are harder for us, okay? So because there are three types of passages, charts and graphs, experiments and fighting scientists, we can start to kind of figure out as we're doing more and more practice which ones we're great at and which ones we just, suck, right? Things that are just hard. Like, for example, for me, I find charts and graph questions to be a little bit easier than fighting scientists, than experiment passages. You might find it to be the other way around. And like we do with all the other question types that we've come across, we categorize them into now, later, or never kind of questions. Now remember, never doesn't mean we'll never do them. Never just kind of signifies that these are the last things that we're going to do. Okay. And some of the common features that we find within our students is that when now passages generally have relatively small tables and graphs, right? Lots of numbers, not a lot of words or symbols. Easy to spot consistent relationships between the figures that they give us, right? And short answers that give us numbers or give us kind of general like yes, no, increase or decrease. And if you haven't seen those before, we'll see a couple of those today, okay? And the questions don't fit into a neat category like we're used to seeing on the reading test, but it's still worth knowing that there are certain commonalities within the questions. Some questions are going to have us look up values or relationships, right? So according to table 2, according to figure 1, right? Some of them are going to ask us to make predictions. If this happened, then what else would happen? Some are going to ask us, well, if this factor changes, what else will change? And some will ask us to draw conclusions based on the information that they give us. Okay? And you can't, just like in the reading section where you can't let one hard passage just really suck the time, or one hard question really suck up your time. Keep that in mind, right? If you notice that you're stuck in quicksand with regard to a particular passage, well then pick a letter of the day, my friend, and move right along, right? And as always, process of elimination, POE, pretty important, regardless of what section that we're on. Okay, POE is always going to be the way to go, especially if you're stuck, especially if you have no idea what you're doing. And pacing, right? Pacing is just is a very important aspect of this, right? Kind of like all the other sections that we've talked about, we want to finish right on time. We never want to finish too early, right? We want to make sure that we spend the appropriate amount of time that's necessary to answer the question without getting stuck in quicksand. Okay, and here we have just the food for thought with regards to the raw score scaling chart. Okay, and if you'll notice, like if you missed 5 questions, what would your score be? Well, if you missed 5 questions, you would be at 29, right? But then, just 1 or 2 more questions here and there is going to definitely help us. Now, what you start to notice about these things, about these scale charts, is that this one, the scale is pretty steep, right? It's pretty steep because the science section isn't that hard, okay? And because of that level of difficulty, so kind of loose, it's easier for students to do well on the science exam, or at least better, okay? Be prepared for the swings, right, from the difficulty from test to test in the science section. What I mean by that is some tests will have harder passages than other tests, and we're not going to lie, right? But the curve evens out that swing within those questions. So how you would do on one test, the score that you would have gotten would have been the same score that you had gotten on another administration of the test. Okay, all we can do is to avoid careless errors. Now, as with everything else that we've done, we have a basic approach to the science section. And the first thing is that if there are figures, we're going to work the figures. And by working the figures, I mean mark any sort of trends, mark any sort of consistency or anything that we notice, and also keep note of the units that are being used to measure. Okay? Then we're going to go right into the question, and we're going to look up the answers and read only what I need to read, if I even have to read. And generally, I like to save those reading questions for the last, because I'm just like, dude, that's going to take up a little more of my time. I'd rather spend my time efficiently answering questions that I can get correct. Okay? Then I'm going to work the answers. And especially on tough questions, I'm going to definitely work the answers. And it's all about process of elimination. Okay? If you don't know what to predict, if you don't know what the right answer is going to look like, then go right into your process of elimination and eliminate based on what you know to be true based on the experiment itself. Okay? So let's take a look at the first step. The first step is to work the figures, right? So if I look at this, right, forget all this stuff here, okay? All this stuff is kind of necessary, okay? But what are the variables here, okay? Well, the variables here are solubility and temperature, okay? Right? And the units are, solubility is what? Grams of solute per 100 milliliters of water. And the temperature is just degrees Celsius, okay? And then what is the temperature doing? Increasing or decreasing? Increasing. They're all going up, right? It's going from 0 to 90. Solubility is also doing the same. It's increasing, okay? And what directions are the curves generally headed? They're going upwards. And what type of relationship is this? It's a direct relationship. And you don't even need to know that it's a direct relationship. You can just be like, dude, when one goes up, the other goes up. Perfect. That works, okay? Cool. All right, so now that we've worked the figure, let's work the question now, okay? Now, question number 36 says, based on the figure, we got to look at the figure. As temperature increases, the solubility of KNO3, without even looking, my friend, because we know that as one goes up, the other goes up, it's going to increase. There was no funkiness, right? None of the curves went up and then down and then back up. They were all going up in a nice, consistent manner. So I know that KNO3, without even looking at my chart, is going to go up. Okay? Cool. Now, question number 37. It says, according to the figure 1, KNO3 and NH4Cl have the same solubility at what temperature? Now, some of you guys might be freaking out going, well, I don't know what the solubility means, man. I got to read this, right? No, forget that. Let's just take a look, okay? And let's take a look at the figure. And it says, well, I have solubility on this side, right? And the question is asking me about KNO3 and NH4Cl. Well, KNO3 is right here, and NH4Cl is right there. And look, they match right there. Odds are they're going to have the same solubility at that temperature, which is like 20, like 28, 29, high 20s, right? Cool. Well, good. They don't give us actual numbers. They give us range, right? Well, it's definitely not going to be 10 to 20. 20 to 30? Yes. And put a check mark. 30 to 40? Heck no. Right? And the solubility of KNO3 and NH4Cl are not equal at any temperature? Nope, that's not true. So B is my answer. Okay? Now, question number 38 has a lot of words. I don't like words, especially when I'm on a roll like this, right? When I'm on fire. So let's take a look at question number 38. We're going to come back, 39. We're going to come back to 38 because it requires a little bit more reading. It's probably going to take up a little bit more of my time. It's probably going to give me a little bit more of a headache. So why not just try to go for the ones that have short, easy answers, nice, sexy little numbers for me to work off of, okay? By the way, if the word sexy offends you, I do apologize, but I'm probably not going to stop. Question number 39. Based on the figure, at 100 degrees Celsius, the solubility of HgCl2 would most likely be what? Okay? So let's go to the figure, and let's go to at 100 degrees Celsius. Ooh, wow. Dude, we don't go up to 100. We only stop at 90. All right, well, let's relax. Let's figure this out. So we're looking for HgCl2. Cool. All right, so that's this one, and the curve's pretty steep. So if this was 100, I'm just ballparking at this point, right? So at 90, the solubility was around 40-ish, early 40. So odds are it's going to jump up into the 50s, right? Okay, cool. Well, it's not going to be 45 because that's a pretty, like I said, it's a pretty steep curve, right? Okay, so it's probably going to be around 55-ish, okay? So 45 is too low, 35 and 25 are too low, so A is our answer. Question number 40. On the basis of the information given, how many grams of NH4Cl can be dissolved in 200 milliliters of water at 70 degrees Celsius? Okay, so at 200 milliliters of water, that's only giving me 100 milliliters of water, right? At 70 degrees Celsius. Well, let's use common sense, okay? So if NH4Cl, which is right up here, okay, at 70 degrees, sorry, that line is not straight, can dissolve 60, can 60 grams can be dissolved, or 60 grams of solute per 100 milliliters of water. Then at 200, it's going to be double, right? We're doubling the water, so you might as well just double the grams, right? Common sense. So at 70 degrees, it's 60. So at 200 milliliters of water, so then it's probably going to be 120 in this case. Okay, cool. All right. So, we did not get to question number 38. So let's take a look at question number 38. And question number 38 is wordy, but let's see how far we can get along. And it says a solution is saturated, okay, and that's italicized, when the concentration of solute is equal to the solubility at that temperature. Okay? So what that means is that it's considered saturated when the concentration is equal to solubility. Okay. Now, if a saturated solution of copper sulfate at 20 degrees was heated to 80 degrees, okay? So at 20 degrees, it's a saturated solution, and it's heated to 80 degrees, okay? All right, so if it's heated to 80 degrees, okay, remember, in order for something to be saturated, it's got to be, the concentration has to be equal to the solubility at that temperature. If the temperature increases, right, would the concentration also increase? No. This requires a little outside knowledge, but we do know that concentration is essentially just the amount of molecules or molecules of a certain substance within the water or the total substance, right? So if the temperature increases, does that affect the concentration? No. The concentration does. It's not as if we increase the amount of CuSO4 here, right? We're really just still dealing with the same number of molecules at 20 degrees as we were at 80 degrees. So if the concentration was saturated, or if the concentration of the solute is equal to the solubility at 20 degrees, the concentration isn't changing at 80 degrees, but the temperature has changed, right? So that they're no longer equal, okay? Because at 20 degrees they're equal, at 80 degrees they're not going to be equal. That's all I know. That's all I can infer, okay? So my answer right off the bat is is a no. Okay, so if it's a no, right, then I can get rid of F and G. Okay, because no, and then so because I know that because of the temperature change, right, and it's not going to stay saturated because it was saturated at 20 degrees. It's not at 80 degrees. The concentration isn't changing. So there you go. So now we have H versus J. H says no because solubility is unaffected versus concentration is unaffected. Well, then we just say that concentration wasn't affected because concentration doesn't increase or decrease with the temperature. Concentration increase is the amount of molecule. Great. So we can get rid of H because H doesn't make sense, and J is our answer. Okay. All right. So how hard was this? Not too bad, right? We didn't do a lot of work. We didn't actually even have to do any real reading, right? So now let's jump into some kind of like an understanding of the curves, of the tables and things that we're going to look at. Okay. So let's take a look at the first curve, and this curve is referred to as an inverse curve. An inverse is inverted. As one goes up, the other goes down. Right? This curve here is just flat. There is no change. This is a bell curve. Okay, if you don't know what a bell curve is, that's cool. You don't need to. And the last one is just a hot flaming mess. Okay, you can substitute any word you want for that F. Okay. Cool. All right. Now let's take a look at at a table and see what we can see. All right. So table 1 here. I have temperature, I have density, vapor pressure, and heat of vaporization. I don't know what vapor pressure is. I don't know what heat of vaporization is, but I do know the trend. So what is the trend for temperature? It's going from 0, 2, 4, 6, 8. It is going up. Okay. The trend for density is that it stays flat. And the trend for vapor pressure, 4, 5, 6, yeah, it's going up. And heat of vaporization, well, they're all 2, 95, 91, ooh, it's going down. Okay. And this one, the heat of vaporization, you want to be careful with because even though it doesn't look like it's going down, or it might look like it's all over the place, if you look real carefully, it is in fact going down. Okay. So let's give it a shot. Let's give it a whirl on an actual passage. Okay. So it's let's take a look at table number 1. And what are the variables in table number 1? Well, first we have velocity, radius, and frequency. I don't know what any of this is referring to, but I know that those are it. Okay. Now velocity is going up, the radius is going up, and the frequency is staying the same. Okay. Let's take a look at the second table. The variables here are magnetic field strength, and I'm just going to write MFS. I have the radius, and I have frequency. Okay. And MFS, it looks like, is going up. Radius is going down, and frequency is going up. Okay, cool. So that's the relationship. And how does experiment number 3 differ from experiment number 2 or experiment number 1? Well, velocity. Let me just take a look here. So velocity is swapped. With MFS. Okay. And the frequency changes, right? Okay. Cool. Now, just kind of real quick taking a look, I'm going to say that table 1 could possibly be at an MFS of 1, just because the frequency is 27,952, and all my frequencies here are 27,952. So I'm just going to make a note. Maybe MFS of experiment 1 at 1. Okay? Maybe. Who knows? It's just something I can infer from that. Okay? Alright, now let's take a look at our questions. Okay? Question number 18 says, based on the results of experiment 1, if an electron were shot into a cyclotron with a velocity of 5,000 meters per second, the radius of the orbit would most likely be what? Okay? So it says experiment number 1, so let's take a look at the first experiment. Velocity here goes only up to 2,500, but that's cool. We can use common sense. We can follow the trend. So if it's shot out at 5,000, the question is asking me for the radius. The radius here stops at 14.2 at 2,500. So at 5,000, what do you guess? That's right, 28.4. Double the velocity, double the radius, right? Okay. Cool. Question number 19. Based on the results of experiment 1 and 3, the magnetic field strength used in experiment 1 was most likely, I feel like I already kind of predicted that. Because of that swap and because of the data, I was able to infer that the MFS for experiment number 1 was probably at 27,000. The MFS was probably at 1 because according to table 2, at an MFS of 1, I had a frequency of 27,952. That's going to be C. So number 20, lots of words. Going to come back to it, okay? 21, if at all, how, if at all, would the results have been different if a proton instead of an electron had been used in experiment number 3? Great. I got no idea. I mean, I know what a proton is, but I don't know how that would affect that. Well, we can't skip 2 questions in a row, so let's give that a try. All we got to do is look for the word proton, okay? So I'm looking. Let's see. Do we see protons here anywhere? Anybody? Oh, protons. Okay, cool. So the scientists then performed exactly the same experiments as the first one, but replaced the electrons with protons, which are oppositely charged. So that's what I know. And the scientists obtained identical data, but notice that the direction of the orbit was clockwise. So proton, clockwise. Let's take a look. So how would the experiment be different? The frequency would stay constant. Maybe. The direction of the orbit would be clockwise. Ooh, I've seen that one. So A is a maybe. B is nice and sexy. C, the radius. Well, C, the radius and the frequency, I don't know. I don't know how the protons would have affected that. D, the results would not have been different. We got B here. B is going to be the one that works for us, okay? All right, so let's take a look at question number 22. And number 22 says, which of the following is the most likely explanation for the result of experiment 3? As magnetic field strength increases, orbital radius does what? Right? Radius goes down, right? So radius decreases. Cool. So I can get rid of F and G. So radius decreases. Oh, frequency decreases or frequency increases? Let's take a look. Frequency is increasing. So I can get rid of H and J is my answer. Okay. Let's take a look at question number 23. 23 says, a muon is a particle that has the same charge as an electron, but is approximately 200 times more massive. Based on the experimental data, which of the following could be concluded about a muon's orbit if the muon were shot into a magnetic field strength of 1 microtesla at orbital velocity of 1,000 meters per second? Okay. All right, cool. So, what do I know about a muon? Well, according to this, a muon is a particle that has the same charge as an electron. Well, protons have a different charge than electrons, and they went clockwise. So muon, electron, counterclockwise, probably the case. So I don't know much about the frequency, okay? But I do know about the orbit. And I have 2 answer choices that deal with the orbit. The radius is the same as the frequency. I don't know much about that because of the different, when you use different things, okay? But I can't, what the heck happened there? Okay, so let me put that back up. But I do know about the direction, okay? The direction is going to be counterclockwise because if a proton goes clockwise, then it has to be, then it will be the opposite, right? Okay, cool. So then the answer for this is B. Okay. Now let's take a look. Let's take a look at question number 20. And number 20 says the period of an object's orbit is defined as a reciprocal of the frequency. Okay. So reciprocal is just flipping it over, right? So according to the information provided, which of the following would most likely provide the greatest period, right? So whatever the period is, and a period is just the reciprocal of the frequency. So we're going to look for the frequency, the one that has the largest frequency, right? Okay. So the frequency is going to be, let's see, what do we have here? Okay, so if I take a look at my answer choices, F says an orbital velocity of 1,000 meters per second and an MFS of 2. Okay, so let's take a look, okay? So 1,000 meters per second and an MFS of 2. Alright, so at an MFS of 2, I don't know how the orbital velocity, I don't know how the orbital velocity really helps, because the orbital velocity gives me all the same frequency, but I do know the MFS is a little bit, does kind of change the frequency. So I'm not going to focus too much on the velocity just yet. So F says MFS of 2, so that gives me a frequency of 55,000. 4 microtesla gives me 111,000. Okay, 1 microtesla gives me 27,000, and 0.25 microtesla gives me 6,000. Well, 1 over 6,000 versus 1 over 27,000 versus 1 over 115,000. Which one is the greatest? That's right, 0.25. J is my